Well, good afternoon, OCP community. My name is Cam Turner. I am the Director of Advanced Technologies at Cool IT Systems. Today, I'm going to talk to you about the work that we're doing on the RPU, just give an update as to where we're at. So as some background, just wanted to remind people who were previously at the Global Summit, and also some of the new people who may not have heard about this topic. So we had planned to debut and showcase the air-assisted liquid cooling, or AALC, concepts at the OCP Global Summit in March. Of course, due to the pandemic, that event was shifted to the virtual summit, where John Fernandez of Facebook, Hassan Alyssa of Microsoft, and I introduced the concept of AALC and why this is of interest to the OCP community. So the concept of AALC is to utilize the superior heat transfer characteristics of liquid cooling to grab the heat right at the source, capture that energy in liquid, and transfer it to a large liquid to air heat exchanger. In this scenario, cold plates can support a higher component power in less U space as compared to traditional air heat sinks, which in turn enables higher power servers, which then rolls up into higher power, higher rack densities. So while this does not capture the full benefits of direct liquid cooling, in that it still relies on the facility HVAC to remove the heat from the data center, it does offer to extend the life of the existing air-cooled facilities by supporting these higher powered liquid cooled SKUs from silicon vendors. So let's go through a quick example just to show how AALC works on the block diagram on the left. Starting at the IT gear, we supply warm water. So this is above ambient air temperature coolant, and that travels through the cold plates, capturing the heat from the IT gear. The coolant from each node is then combined in the return manifold and transported using tubing to the remote liquid to air heat exchanger. At the remote liquid to air heat exchanger, cold air from the facility passes through it and captures the energy that was in the liquid and transfers it out into the hot aisle, which in turn is, of course, lowering the temperature of the coolant. So this now cycles back through the RPU, and this cycle starts again. So you can see in the block diagram, the RPU is powered from the rack, and it can in turn power the remote liquid to air heat exchanger. The RPU is also what is connected into the rack manager or the BMS system, and it's responsible for all aspects of control and monitoring for the cooling solution as a whole. So this includes the remote hex as well as the RPU. So the two sample implementations that we were going to show are shown on the right-hand side of the screen. The white rack would be a rear door heat exchanger-based liquid air AALC solution. This is the example that John showed in his presentation before. In this scenario, the RPU is going to sit in the bottom for you, and you'll have airflow going through the IT gear and going onto the coil, which is a full 48U on the rear of the rack. The black rack on the far right is an adjacent rack, liquid air heat exchanger. In this scenario, again, the RPU sits in the bottom for you. There's space for a power shelf at the top, and the remainder of it is the coil. And in this scenario, the airflow goes directly onto the coil, as all the IT gear is adjacent in another rack. So Cool IT has been working with Facebook and Microsoft to define a specification for the RPU. We are prototyping solutions to ensure the specification is both technically feasible and commercially viable. Within the specification, the areas that are covered are the physical dimensions, the interfaces, performance targets, monitoring and control requirements, and operational requirements. The RPU has been designed to fit within 4U of standard 19-inch EIA rack, such as the OCP Project Olympus rack. As the volumetrics are larger in the open rack architecture, an adapter frame has been designed to allow for standardization of the chassis components. The volumetric dimensions are currently 175 millimeters high, 488 millimeters wide, and 800 millimeters deep. This is a little bit in flux as we're working on a few remaining concepts. Keep-out zones have been defined for interoperability between rack architectures and to allow for maximum flexibility between RPU vendors. Sorry, excuse me. So the keep-out zones that have been defined include the network backplane, the BlimeMate rack manifolds shown on each side, both the left and the right side there, as was discussed by Glenn earlier. The open rack V3 bus bar, and also a spot for the power Project Olympus PMDU unit. So, and then in the AC version, basically where the power sockets for the PSU are located, where the open rack V3 bus bar resides. And finally, on the liquid interface, we're utilizing Stauble's CGB20 plugs as there is no large enough UQD to support the flow rate required for an entire rack. And this is something that will be investigated moving forward with the community as a whole, is standardizing on a larger quick disconnect. So the preliminary performance numbers, nominal performance was targeted at 40 liters per minute, and this has been achieved at 138 kPa, so or 20 PSI for my friends in the States. This number, specifically the flow rate, represents 1 liter per minute per kilowatt cooling, and the RPU has been designed with enough pressure head to accommodate multiple design configurations for the coils, manifolds with the larger and smaller QDs, and also a variety of different passive cold plate loop configurations. The maximum pressure head achieved at this point with this RPU is 345 kPa or 50 PSI. And power consumption is 305 watts at this nominal performance number. So in this scenario, that puts us at about 1% of the total power of the rack, assuming a 40 kilowatt rack. Now, as John showed earlier, the specs for total power consumption have been defined. So the total solution is to be less than or equal to 5% of the total power of the IT gear. And the RPU is intended to be less than 3% of the total power. So the RPU has several different flavors in terms of input power. There's, of course, the 48 VDC for the open rack V3. 12 volt DC can also be accommodated to support ORA V2. With the ORA V3, the 48 VDC can be passed through the RPU to power the remote liquid air heat exchanger. This allows you to not have to have another connection onto the bus bar. The universal single phase has also been designed in. The plan here is to utilize AC power from the remote hex, as that's actually quite common. However, if the remote heat exchanger uses 48 volt DC, that pass-through connector is available. Power and communications is currently, the connector is currently defined as a Samtec 8-pin assembly, and we'll be going through testing to ensure that that meets all the requirements. For monitoring controls, we have defined 2 control modes. First being differential pressure, the other being coolant supply temperature. So in differential pressure mode, this ensures that the desired flow rate for each chassis is achieved regardless of the number of chassis in the rack. So therefore, when you're servicing a particular server and you disconnect it, pull it out of the rack, the remaining, the flow rate to the remaining chassis within that rack doesn't change. On the coolant supply temperature side, this constant temperature is utilized to ensure that its supplies to each of the cold plate loops remains constant regardless of IT load. So of course, in order to control this, you have to have all the instrumentation defined. So an instrument index has been defined in order to support them. So some of the sensors that are included are coolant supply and return temperature and pressure, flow meter, reservoir level sensors, of course, leak detection, pump control and tachometer readings, as well as others. The RPU also controls the remote hex and gathers and reports the appropriate telemetry from them. So this includes multiple inlet and outlet temperatures, differential pressure across the coil, fan speeds and tach for each fan that is in the system. So next steps, reliability testing on hot swappable pumps. This, of course, to ensure the reliability and resilience required for hyperscalers and end users. Of course, in a situation like this, if the RPU goes down, the entire rack goes down because there will be no cooling. So we have to spend a lot of time making sure that this is going to work as expected. Validation of the control schemes is of course required, ensuring that it is behaving the way we want it to, and also reporting all that information back into the appropriate rack manager and BMS systems. Completion of the engineering validation testing, and then finally a contribution of a specification to OCP. So the call to action slide, which of course we've been seeing throughout the day, just reiterating what everybody else is saying as well, get involved in the different solutions. The advanced cooling solution, of course, being the overall tent of what's going on. The door heat exchange work group that John's been running has, of course, been defining what the rear door would look like for the AALC solution. And of course, the cold plate stream. Cold plates are a key component to this, and we'll be working with all of these groups to harmonize together and put all of the different requirements into a full rack. So rather than just looking at the individual components, the shift will be moving on to the solution as a whole. I have put in links to all the different wikis, and that is what I had for today. I'll open it up to questions.
Thank you, Cam. Folks, if you do have a question for Cam, feel free to throw it into the comments section, put it on the Etherpad. If anyone on the Zoom call has a question, feel free to speak up now while we've got him as a captive answer. Cam, we've got about 55 folks on the call, and you explained it so well. I don't think there's a single question.
I left a bunch of time for questions. Now it looks like I didn't plan my presentation right.
It's all right.
Will,
we do have a question coming in.
Okay.
Don Mitchell. And it's in the FN Virtual comment section here. Is CDU generally recommended supplying a loop of rear door heat exchangers?
sorry, I just opened up the FN. Is CDU generally recommended for supplying a loop of rear door heat exchangers? In general, that is what I have seen as the standard implementation. It allows you to decouple the facility liquid to the IT gear, but it's certainly not a requirement. You just have to make sure that you are monitoring the wetted materials appropriately.
Perfect. So I see Don actually joined the Zoom call. I have a suspicion it's because he'd like to talk this through. Don, can you hear us? It's like you're on mute, Don.
Okay, so
We can hear you.
We can hear you.
very much now. And I apologize, Cam. I kind of cut you off there as I was trying to link in. Learned a lot about the process of signing in to make a comment. So this is a good trial run for me because I'll be talking on Friday. But one of the things I did want to kind of highlight is I know that some rear door heat exchangers get connected straight to the existing loop. And in some cases, can you hear me?
Yes. Hey, yeah, we can hear you.
Hey,
fine,
Don, you're talking on Thursday, right, buddy?
Yeah.
Did you say Friday?
It's Thursday. Hold on a second. I got to figure out what I'm doing here. Okay, we'll try this again. There seems to be a 30-second lag.
Yeah, you might want to kill your the FN tech window.
Yeah, Don, go ahead and mute the FN virtual tool while you're talking on Zoom.
Yeah.
Clear that.
How about now?
Sounds good.
Okay. So yes, we will be talking Thursday. This thing's gonna.
So I think the question was, do we generally recommend supplying coolant directly to the rear door or via a CDU? I've seen both. It really would depend on the overall infrastructure of the data center that it's going into. Dale might have a comment on that, actually.
Yeah, I do. I think that, we're really at the edge in rear door cooling in terms of free cooling or compressorless cooling. So I'd like to see the minimum number of heat exchangers between the tower and the IT equipment. So I think it depends on how you define a CDU. I mean, if the CDU is the plate and frame heat exchanger and the pumps between the tower and the rear doors, then we've got one. But if you're adding another CDU, like in the data center as opposed to in the mechanical room, that's a problem because you're losing the ability to free cool.
Yeah, a very valid point. The stack up of all those efficiencies will get you eventually.
So Don jumped ship, huh?
I think we may hear more from Mr. Mitchell on Thursday. Dale, I'm glad you hopped on to ask that question since you're our next speaker here. Cam, thank you so much for your presentation and for the Q&A there.
Awesome. Thanks everybody for your time.